Welcome to Lecture 4 of the EET K105 course. Today we're going to be covering Chapter 5 in the text. We're going to be talking about series parallel and series parallel circuits. First, we're going to review energy and power, especially how it relates to motors. So, again, today we're going to talk about series circuits, parallel circuits, and series parallel, but first we'd like to review energy and power. Suppose we have a 20 horsepower motor that's 85% efficient. We want to find the input power. The 20 horsepower, by the way, is the output power, in case you didn't know that. So if we take 20 horsepower times, we're going to convert this to kilowatts, so it's 746 watts per horsepower, and that will equal to 14.9 kilowatts. And we can use our calculator to find that. If we multiply 20 times 746, and there you go, 14,920 watts, which is 14.9 kilowatts. Okay, so we got the power. We're going to take the we know the efficiency that nu equals power out over power in, or 0.85, which is our efficiency, equals 14.9 kilowatts over power in. So power in is equal to 17.5 kilowatts. We can draw the power diagram as we did last time, like this. .9 kilowatts as the output. And 17.5 kilowatts is the input. And our lost power is 2.6 kilowatts. And that's lost as heat. If we look at what the motor looks like, we got a motor shaft. And that rotates with a certain RPM. And torque. It's an M there, and torque. And between the RPM and the torque, that determines the output power. which is 20 horsepower. The power loss, as I mentioned before, is due to heat from the windage, the windings of the motor. Some of it is due to that. And there are other losses also in a motor, being friction, and we'll talk more about that later. Let's look at another example. If we have a 5 horsepower motor and we have Vn is equal to 24 volts DC and a current of 190 amperes. We want to find the efficiency. New. So if we look at this, we can draw a chart like this showing our input power, output power. So Pn is equal to 190 amps times 24 volts equals 4.56 kilowatts. And our output power is 5 horsepower times 746 watts per horsepower, and that equals 3.73 kilowatts. And what we've done in effect here is we've transitioned from the electrical to the mechanical. So if we go to and calculate our efficiency, its efficiency is P out or P in to 373 kilowatts over input power of 4.56 kilowatts, and that equals 82%. You're going to see a lot of problems like this as we go forward on the quizzes and tests. So I recommend that you kind of look at these closely and make sure you understand how to calculate powers and energy. Horsepower equals pound-feet or foot-pounds, as torque is often called, either one, times RPM divided by 5252. Going back to our chart, we find that we have the electrical, as I mentioned before, and the mechanical sides. But we converted the mechanical to electrical. That's why we went from horsepower, which is mechanical, to kilowatts. If they're both converted to kilowatts, then we can calculate efficiency. We have to have the same units, though, when we calculate efficiency. So let's draw a series and parallel motor connection. Start out with a voltage supply, 18 volts DC, hooked to 3 motors in series. And one thing we notice is that we have current flow through the loop, so we have the same current in all motors. And by the way, you're going to have a lab next week on this very subject. Then we have the parallel setup. We have a voltage source, plus and minus. And we have a parallel circuit here. And we have a 6 volts DC. And we have 3 motors. Actually, I'm going to erase this. 2, 3 motors. And in this case, because it's a parallel connection, we're going to have the same voltage across all 3 motors. So in the case of the series connection of the motors here, we said that the sum of all the voltages are 0. In other words, the sum going around the loop, actually this way, in that direction, of all the voltages equals 0. And that's Kirchhoff's voltage law. Parallel setup here, parallel circuit. This is the Kirchhoff's current law, and we say that all this, we sum the currents, and that equal to 0. Equals 0. So the sum of the currents in equals the current out. Now let's take a look at some series resistors. Draw a little circuit here. Battery. We have a 10 ohm. And another 10 ohm. And a 12 ohm resistor. And we have a 12 volt voltage source, battery. So the formula for the total resistance of a series circuit is resistance total, we call it T, is R1 plus R2 all the way up to R sub n. Because you can have really an infinite amount of resistors in series, or n amount. Okay, and that would be our total is equal to, in this case, 10 ohms plus 10 plus 12, which equals 32 ohms. So we could draw an equivalent circuit now with a single resistor, and this is how we do that. We have our 12 volt source, and this looks like a single 32 ohm resistor. Okay, so let's now look at parallel resistors. We have a circuit like this, battery. And we'll use 3 resistors here. This will be a 12 volt source. So R1, 30 ohm. R2, 47 ohm. And R3 is a 22 ohm. So in the case of a parallel configuration like you see here, the R total is equal to 1 over R1 plus 1 over R2 plus to 1 over Rn. So this is one way to express the total resistance of a parallel circuit. Another way to express R total is by this expression, and then there's a third way by this expression. So if we plug in the values for the resistor from our example here, we have 1 over R total equal to 1 over 30 plus 1 over 47 plus 1 over 22, which equals 9.9 ohms. And we could calculate that with our calculator here. So we have 30 inverse plus 47 inverse plus 22 inverse equals, and then we'll inverse that, and equals, change it to there you go, 9.9 ohms. How about that? As another example, we have a series circuit here which has 4 resistors in it. R1's 14 ohms, R2 is 7 ohms, R3 is 20 ohms, R4 is 15 ohms. So to find the total resistance, we just add them up. 14 plus 7 plus 20 plus 15 is 56 ohms. Now we can redraw this circuit as a voltage source and a single 56 ohm resistor. So the current, if we wish to calculate that in the loop, would be 28 volts divided by 56 or 500 milliamps. If we want to calculate the voltage on R3, it would be simply 0.5 amps from here times 20 ohm is 10 volts. And we want to calculate the power on R3 using our triad chart here for power. There, so you can see it, would be 0.5 amps times 10 volts, or 5 watts. Another way to calculate the power on R3 is by our formula, I squared times R. So that would be 0.5 amps squared times 20 ohms is also 5 watts. We get the same answer. So you can see that there's multiple ways to solve these circuits. In a follow-up class, we'll show you how to use a voltage divider, which makes this even easier to solve this type of a problem. Another example, we have a parallel circuit, and we have three resistors, and so we can calculate our total as 1 over our total is 1 over 8, 1 over plus 1/4, 1 over 4 plus 1 over 3, and that equals 1.41 ohms. And we can calculate that again in our calculator here. So if we have 8 reciprocal plus 4 reciprocal plus 3 reciprocal, that equals, and we take the inverse of that, equals, and change that to decimal point. It comes out to 1.41 ohms. Very good. I think with a little practice, it's not, I guess, very trivial when you're calculating resistance from a parallel circuit. But I think once you get used to it, you'll feel more comfortable with it. We can also calculate the source current, which is the voltage source 13.8 volts over our total, which we just calculated as 1.41, and that gives us 9.8 amps of current. Now let's look at the current through R3. So that's IR3 is equal to 13.8 volts divided by 3, and that equals 4.6 amps. What is the voltage on R3? Well, this circuit only has 2 nodes here at the top and at the bottom. So the 13.8 volts is across all 3 resistors. So the voltage across R3 is 13.8 volts. Now let's calculate the power dissipated by R3. So power of R3 is equal to 4.6 amps times 13.8 volts, and that's equal to 63 watts. Another way to calculate the power across R3 would be power R3 equal to E squared over R equals 13.8 volts squared over 3 ohms, and this also equals 63 watts. Same answer. How about that? And now I'd like to talk about Kirchhoff's voltage law. Basically, that states that if we go around the loop, the voltages will sum to 0. And that's this expression right here. The sum of the voltages around the loop equals 0. So in this case, we're going to pick an entry point here. If I get out of the picture here, and we'll go around the loop in a clockwise direction in this case, and we'll start with minus 10 minus x, since this is the unknown here, plus 18 equals 0. Solving for x equals 8. So there are rules for polarity going around the loop. If you're an observer here and you go around the loop and you go toward the plus side of a battery, then that would be plus 9 volts. Similarly, if you approached the battery from the negative side, it would be minus 9 volts. Let's look at an example. If we have two voltage sources here, one 10 volts, one 2 volts, I'm sorry, 3 voltage sources and a third, 3 volts, we will go around the loop starting here. So we have plus 2, minus 10 coming in again from the minus side, and minus 3 plus AB equals 0. So minus 11 plus, this is plus voltage across AB equals 0. So the voltage across AB is equal to 11 volts DC. Let's look at another example, shall we? Voltage source here. R1. And resistor R3. .24 volt DC power supply, and we have a voltmeter out here measuring the voltage with leads. Plus, we have a red and a black lead on our meter. That's reading 15 volts DC. So if we're a little observer here, looking in here, we go around the loop. It's minus 24 minus VR1, since that's what we're looking for here, plus 15 equals to 0. The voltage across R1 is equal to 9 volts DC. For example, we have this circuit, and we want to solve for the power of R3. Redrawing this looks like this. 10 ohms. R2, 10 ohms. R3. R4, 10 ohms. That looks a little simpler, doesn't it? And we're going to redraw it again to simplify it even further. R1, 10 ohms. And we've combined R3 and R4, and this becomes 20 ohms. we can put a box around here now. Remember our R box. And we can solve for 1 over R box equals 1 over 10 plus 1 over 20. And if we calculate that, which we won't, you can trust me on this one, 6.6 ohms. So now simplifying even further, we have only two resistors. 10 ohm, our 6.6 ohm. We can combine the 10 and the 6 to a single resistor of 16.6 ohms. So if we look at the full circuit, we have voltage source, 16.6 ohms. We have the source current, I sub S. And this is 100 volt. So I sub S equals 100 over 16.6 and equals 6 amps. So going for original configuration, our current, source current, is 6 amps. That flows through R1. We can draw a voltmeter across R1. Put it over here. So the voltage across R1 is equal to I sub S times R1, and that equals 6 times 10. That equals 60 volts. Going around the loop with the KVL, and I didn't indicate that this is 100 volts DC. Sorry about that. Going around the loop here, we have, starting in this direction, we got minus 100 plus 60, which is our voltage across R1, plus voltage across R2 equals to 0. So voltage across R2 is equal to 4 volts. Redrawing the right-hand side of the circuit, we have 40 volts. In R4. Our 6 amps of current going through the loop. We have R2, 10 ohms, R3, and R4. So we want to calculate the current through R2. That's 40 volts over 10 equals 4 amps. So we have 4 amps of current going through the R2 leg of this circuit. I want to calculate the current for R3. And that equals the current going through R4, since it's the same, is 40 divided by 20 equals 2 amps. So we have 2 here. And if we look at the currents flowing out of this node right here, we'll see we have 6 amps going in and we have 4 amps leaving the node, as well as 2. So 4 plus 2 equals the 6. Next, we want to calculate the power on R3. So we'll call that power equals I squared R equals 2 squared times 10, and that equals 40 watts. So, just in summary here, we started with a complex circuit. We simplified it a couple of times. Later we'll talk about voltage dividers and current dividers, which will simplify our circuits. For our last exercise here, I have a small circuit. For our last exercise today, we'll take an R total equal to 10 plus 2 in parallel, and that's the parallel symbol, 3 in parallel with 5 ohms. So let's draw that circuit. Looks like this. 10 ohms parallel with 2 ohms parallel with 3 ohms and parallel with 5 ohms. So we can calculate that value of the parallel combination would be 2 inverse plus 3 inverse plus 5 inverse equals, and you inverse that, equals 0.97 ohms. Okay. So our total equals 10 plus 0.97, and that approximately equals 11 ohms. So that is it for the day, and we will see you next time.